Hello and welcome to this week's installment of Between Two Fake Trees. I'm Peter Schneider, and I'd like to welcome Alex Milne from RF Venue. Welcome, Alex.
Thank you very much, Peter.
Thanks for joining us.
I'm so glad to be here. I've caught a few of the episodes before. You've had some very interesting people on talking about relevant and useful topics, and I'm glad to be part of it myself now.
Absolutely, yeah. I've been following this product. So the product we're here talking about is the OPTIX, which I don't know if we can see it.
There's probably a close-up here on this one.
Yes.
Yeah.
We've actually set up the OPTIX, and first let's talk about what is the OPTIX?
Yeah, well, I thought maybe we could start, if it's all right with you, with just an overview of the technology that's inside these boxes. Please. Generally.
Yeah,
because it's not necessarily something that every sound professional or production audio professional is familiar with.
Right.
So the OPTIX is a miniaturized and more affordable version of what's known as RF over fiber optic technology. And RF over fiber systems have existed for decades. Mm-hmm. They began in the telecommunications and data industries for doing things like building the internet, important things like that, and transmitting voice signals very long distances. And essentially what they do is convert radio frequency energy, mm-hmm. Coming from some sort of source, a transmitter or receiver, energy collected from an antenna in the air, and then it converts it into an optical signal and sends it through a fiber optic strand very far, because there's very little inline attenuation with fiber optic systems.
So a person who has to carry RF signals over a long distance would be, say longer than what RF normally would go through in the air, could use a system like this.
Right. So traditionally in professional audio and wireless audio, the cable medium of choice is the coaxial cable, which we're all very familiar with. Coaxial cable has been around for a very, very long time, maybe 100 years.
Yes. You're really familiar with it when you coil it up after it's been in the streets of Brooklyn.
Right. So coax is good, and there's lots of different types of coax, but there are certain shortcomings to coax. The largest of which is probably that it has, depending on what type you use, it has significant inline attenuation. Right. So RG8X, for example, which is a standard that a lot of audio professionals will use in commercial scale deployments, loses about 1/10 of a decibel per foot, mm-hmm. or 10 decibels per 100 feet. Given, it depends on what frequency you're using.
Sure, of course.
So you can see very easily with those numbers, once you want to, say, remote an antenna or distribute a signal, an RF signal via coaxial cable, a distance that's greater than, say, 100 feet, you're going to run into some pretty strong, a lot of loss of gain.
Sure.
And you can compensate for that with amplifiers, mm-hmm. Either at the receive antenna site or by boosting the signal, if it's a transmitter, by boosting the transmitter signal, or chaining inline amplifiers together.
And I've had to run RF over coax for mm-hmm. like 300, 400 feet, and you get into inline amplifiers, and then of course really low loss cable, which is not very flexible and very heavy.
And it was very expensive.
And expensive. It was thousands of pounds.
Yeah.
And in this particular installation, it had to be plenum rated because we were going
mm-hmm.
in the ducts.
Yeah.
So, I mean, it was incredibly expensive.
Right.
And I wish that there was an affordable option to do it with some other kind of cabling.
Yeah. So coax, you can do what you're talking about, which
Right.
is remote antennas or an antenna system like a distributed antenna system, which we'll define later if people aren't familiar with what those are.
Sure.
You can absolutely use coaxial cable to travel lengths of 100 feet or beyond, 200 feet, 300 feet, even thousands of feet, but it's going to be expensive.
And backbreaking.
It's going to be very bulky.
Yep.
And because of the amplification required, you really need to know what you're doing to manage your gain structure, because each amplifier that you add, you know, the noise floor starts to go up.
Right.
And as the complexity of the system increases and the length of each branch of a distributed antenna system increases, it becomes increasingly more difficult and troublesome to use coaxial cable to distribute antennas. Yeah. With fiber optic cable, you basically have none of the shortcomings when it comes to signal loss of coaxial cable. For example, the Optics uses single mode fiber optic cable, and I've got a strand here. We're using, for demonstration purposes, we're using TAC 12, I think, right?
Yep.
So this is a bundle of 12 individual strands of single mode unidirectional fiber optic cable, but you don't have to use tactical fiber. This would be much more expensive than something like this, which is what we normally recommend, which is just a single strand of 1310 nanometer single mode fiber terminated with ST connectors on both ends.
Now, if you were to use this in a temporary installation, like on a film set, if you had to run it to set, say, 200 feet or 300 feet, tactical fiber would be the way to go. Right? I mean, this stuff on its own isn't strong.
So sure. So I mean, well, this has. I feel like we're on QVC here, but just look at that bend radius, Peter.
Yeah, right. That's
Have
incredible.
You ever seen? Incredible.
It's so curvy.
But yeah, this is not something you would want to be throwing around for years. Right. No, you're absolutely right. But this stuff, you can log on. You can go online and you can find a wholesale supplier of fiber optic cables, and you can get it for 25 cents a foot or 50 cents a foot.
Right.
So it's very attractive to people for that reason. And also, you could gaff this to the wall too. You know, it's extremely light, and weight is very important, especially when we talk about cart systems and bag systems. 1,000 feet of this, which you could easily do with negligible, no loss at all, almost. You lose 0.003 decibels per foot with 1310 nanometer single mode compared to a tenth of a decibel. So it's like orders of magnitude less loss.
It's
so
fantastic.
you don't even have to worry about it. We have production sound mixers out on the West Coast. I guess their workflows are a little bit different. Often they're stationed outside of a sound stage.
Much farther away, sure.
Some of them have actually ran this miles. We say up to 1,000 kilometers, but you can go farther than that if you want to.
Sure. Let's break it down.
Okay.
So we have, basically it's 3 parts to it, right? We have this part which would, we're saying that this is the set. If you can picture it, imagine this is separated by 1,000 feet. So the set is here, and these are, it's sort of a funny name, right? Because these are the transmitters. But the transmitters are actually receiving from these kind of transmitters.
Yeah.
Here.
So there is a bit of confusing terminology that we should go over. And let me address your first point. So like, what are the basic components of an RF over fiber system? There are 3 of them. One is the fiber optic transmitter. Yeah, okay, and we got a diagram here. This is the fiber optic transmitter, which is a little confusing now. It says transmitter, but it receives whatever RF input you give it.
It's a transmitter from the fiber optics point of view.
Yeah, it's transmitting the fiber optic
To the fiber.
optical signal, and that's why it's called a transmitter.
Right.
But typically, with the optics at least, most of the time we see people putting receive antennas into the RF input, and then the transmitter converts the RF energy into optical signal. And the second component of RF over fiber is the fiber optic strand itself, which is represented by this blue line right here. And then downstream, on the other side, is the third and final component, which is the fiber optic receiver, which takes the optical signal and converts it back into RF, and then outputs it for connection to your wireless receivers or distribution systems.
So if we can get a shot here of what I have in my hand, you can see the receive side. I'll raise up my arms.
Yeah, it's a little bit cumbersome. That's
There we go. And so these are the receive side here.
There we go. Yeah.
And this is the receiver here. And it's literally just the fiber optic is plugged in here, and it converts fiber to coax here.
Yep. And you may have noticed there are two modules on both sides. There are two transmits and two receives, and that's because this electrosonics receiver is a diversity receiver.
Right.
So each optics module can accommodate, if you're using it for receive applications, you can actually put a lot of channels. Say where you were using a receive antenna, you can put up to, we've had PRG, you know PRG,
Sure.
They've put 24 RF carriers of UHFR through one strand. But since this is a diversity receiver, we need two signals coming from two different antennas, and hence we need two fiber optic transmitters that are fed by two receive antennas, which are right here, although we wouldn't normally see whips attached to the transmitters.
Right, so
they would be remoted via a fiber optic cable. Yeah, like that.
So via coax cable.
Yeah, well, this would be a fiber optic. This is just to show coax versus different types of coax you can see. And there we go. So, and then on the other side, you correspondingly need two fiber optic receivers in order to keep the diversity channel A and B intact so that you can deliver them to the receiver or the distribution system.
Understood. So this part is the set. We have our fiber optic transmitters. We're showing it with whip antennas for the purposes of our demo, but normally you'd have them hooked up to paddle antennas or some kind of distributed antenna system.
Yeah, normally.
And then it would go through fiber optic, let's say 1,000 feet, but could be miles, over to the sound cart where it goes from light back to RF into our receivers. We're showing it with one receiver, but normally it would go to a venue system or some kind of multi-coupled group of receivers. And so the real benefit of this is instead of, and I wish I had a low-loss coax cable. Maybe we'll get one later. But they're thick, heavy bundles of copper cable.
They're it's like wrangling pythons.
Yeah. And then if you're doing exterior shots, to run them in the street and then to bring them back, it's just a nightmare. I would do the tactical fiber, and this is so much lighter than coax. And also, you're not dealing with the loss associated with coax.
Right.
Now, you mentioned, and I'm skipping around a little bit, but you mentioned that RF over fiber in general has been around for a long time, but RF over fiber has been around for a while. What sets these units apart?
There are a few things that set the optics system apart from RF over fiber systems designed for data and telecommunications, and also RF over fiber systems designed specifically for wireless audio or broadcasting. One is that a lot of RF over fiber modules, the transmitters will include an amplifier in the front end, right? And amplifiers being, I think, nonlinear devices.
Sure.
They always introduce some sort of noise
Yep.
into your signal.
Right.
So there are no amplifiers in this because we intended originally for it to be used just for receive applications. So you don't need to amplify a receive signal because that's going to be done downstream by your receiver or your distribution system.
That's right.
So if you try and adapt a RF over fiber system that's built for data or for telecom, they're going to have a bunch of noisy amplifiers in there because they may be sending it from one data terminal or base station to another one that's like 30 miles away, right? And that's going to increase the noise floor a lot. And when you try and use it for audio, you're going to have, at best, significantly reduced signal to noise ratio or carrier to noise ratio, and at worst, audible artifacts and compromised audio.
Right.
So that's one thing that differentiates the optics from some other RF over fiber systems that are out there. The other is that RF over fiber is expensive. It's very, very expensive. Almost, as far as I know, everywhere else you can get it, because up until this product, it's been confined to the broadcasting and special events industries. Right. So we haven't really seen fiber optic technology come down from 7-8-figure budget productions and special events. Or sound stages, reality stages, where they have $400,000, $500,000 to put into a distributed antenna system using fiber. Right. In which case they'll contract a skilled specialist. And again, those specialists are very skilled, and there are some things that they can do that the optics cannot do.
Right.
So I'm not putting them down at all.
Right.
But most sound mixers, production sound mixers, don't have $500,000, right, to pay for a fiber optic system.
That's right.
So we stripped everything away from an RF over fiber system and just said, what do we need to keep the excellent long distance propagation characteristics of fiber optic cable, as well as uncompromising audio fidelity. And what we've come up with is a system as a whole that's about $1,000.
Wow.
Right?
So, and is that for two?
So yeah, so one optic system is a transmitter and a receiver.
And for diversity, you'd need two systems.
Right, and and we have an SKU for that. That's a bundled package. You do have to buy your own fiber optic cable, but as I said, it's if you want it to be cheap, it can be cheap.
It can be cheap, but also, and so Joe, thank you for grabbing this. This is low loss coax cable. This is 25 feet, I bet, if that. And it is thick and it is heavy and not very flexible. They do make ones that are more flexible than this, but you get the idea. This is also not cheap. So, 500 feet of tactical cable plus the RF over fiber transmitters and receivers, I think is still much, much better than 500 feet of coax plus all the amplifiers that you're going to need, especially if it's something that you're going to be setting up on a temporary basis. I mean, even if it's semi-permanent, like a reality show or something like that, I think the math is still better. I think this is a better way to do these kind of antenna runs.
Yeah, and there are, math aside, there are some things you can do with fiber optics that you just cannot do with coax. If you want to send a signal miles, you can't do that with coax. If you want to send it kilometers, and if you want to have your cart not weigh an extra, 500 pounds for a 400-foot run of LMR. That's probably LMR 400 or LMR 800.
Right.
You just can't do it, right?
Right. And the other thing is, I mean, look, there's a lot of ways to skin the cat, right? I mean, we could put receivers way far away, and we could do, some kind of outboard, analog to digital converter, and then carry the audio over, an Ethernet system.
Yeah.
But there's something very, very useful about having all of the receivers local to you.
Right.
So, in this system, we're talking about remoting the antennas and then having a small box, this box, by the antenna. This box does need power, but it's happy with 9 to 12 volts, right?
Yep, it's good with 9 to 12 volts. I'm going to talk about that in a second, and I know that we want to. We're running a little bit late, so we want to wrap it up.
Sure.
There's no latency with the optics. So that's a concern for a lot of people.
There you go. Right.
There is physical latency in that the electrical energy needs to travel through.
But we're talking nanoseconds.
Right. We're talking there's no digital. There's not really that much digital circuitry in here that's going to hinder and capture your signal on its way to its destination.
Right.
So I wanted to say that, and a lot of production sound mixers are interested in using this at the remote antenna site, but that site might be like in the Sahara Desert where there's no power supply outlets, and so we often get questions about, can I power the optics with an external battery pack? And there are lots of them available, and you probably know the ones that you sell more than I do.
Sure.
For some reason, those have a output of 14.8 volts. Mm-hmm. So you can't. That's over the limit. This is between 9 and 12 volts DC. So if you are going to use an external battery pack, you can do it, but if it has a voltage above 12, you need some sort of step converter or transformer to step down that voltage into the safe range. We recently had a production sound mixer successfully use one of these remote battery packs using something called a buck converter.
Sure.
And soldering may be involved, but you can do it. But just be careful because you don't want to fry anything.
12 volts. Fair enough.
You don't want to fry anything. I think there's a few, so it sounds really easy, right?
Yeah.
But there are a few things that you have to know in order to use fiber optic, RF over fiber systems safely and effectively, especially if you're using them to transmit high power signals originating from IFB transmitters or IEMs.
So far we've been talking about talent, let's say on transmitters at the remote location and receiving those signals back here, but you're talking about going the other way.
Right. Well, I want to just talk about generally the do's and don'ts of fiber optics, which are very brief. And it's on my computer here. Let me see if I can find it.
I see Diego had a comment, but I don't see a question. Joe, did you see a question from somebody?
Yes. His understanding is that it is not good to saturate fiber signals with too much RF power.
Right. So this is, I think this is exactly what Alex is going to talk about.
Let's pull up this slide here, if you would. Okay. So first of all, thank you to Henry Cohen, who helped me with some of this knowledge. Henry Cohen has been using RF over fiber systems for decades, and he's extremely knowledgeable.
Yes.
So the number one rule with fiber optics is that power management is not optional. So the RF input on the transmitter is very, very sensitive. You can't, with the optics, you can't, here's the RF input, right? Right now there's an antenna, but there's nothing stopping you from just taking a coaxial shorty from an IFB transmitter at 250 milliwatts and plugging it in here. But if you did that would be bad.
Got it.
Because the maximum input is 0 decibel microvolts,
Right.
which is about 1 milliwatt, which is very small when it comes to signal strength.
And that's all RF coming into it. So in other words, like am I getting ahead of you?
Yeah, that's the next point.
right,
But you're right.
sorry.
You're right.
All right,
So
sorry.
no, it's okay. It's okay. So you need to make sure that the power that's coming into the fiber optic transmitter is at or below 1 milliwatt.
Right.
Otherwise, bad things are going to happen. And then the second
It won't
thing.
catch on fire. It'll just overload.
Well,
right?
if you put,
right.
sure, if you put like a kilowatt in, it will
CB
catch on
radio.
fire, yeah. But 250 milliwatt transmitters are not uncommon.
Yes.
Right? So that is too much. That
Yes.
is way too much.
Yep.
And if you're putting multiple carriers into the RF input, it's actually the aggregate or composite power of all the RF carriers combined,
Got it.
which is a little bit counterintuitive to people who have only done RF signal distribution before. But for example, if I had 4 IFBs that were combined using a passive combiner into one coaxial cable, and each of those carriers had an output power of 100 milliwatts,
Yeah.
the fiber optic the fiber optic transmitter input would see the aggregate or the total of power of all those carriers. So it wouldn't see 100 milliwatts, it's going to see 400 milliwatts.
Minus the losses of the combiner.
Right, right. So,
Right.
but you still need to accommodate for that using appropriate attenuation
Sure.
pads or limiters
Sure.
at the input to make sure you're never exceeding that 0 dB threshold.
Right. Fair enough. And then what about the kind of traditional use of it where it's a bunch of talent on set? How do I do the calculations? And we may not have enough time to get into it, but let's say I have 30 talent wired. So they're wired and they're
With mics?
with packs, and those, let's say we set them to 50 milliwatts each pack. How do I do the calculations to know how much RF energy is going to be at that antenna?
That's a tricky one. Because
there's loss
and that's
through the air and loss in the body.
Right. And I don't think that's something that I could answer for you right now. But I will say that is not something that we've had people report back on as being a problem.
Right.
If you're using it for receive applications and your receive antenna is remoted a reasonable distance away from those talent,
right.
Since radio wave propagation through air attenuates extremely rapidly following the inverse square law. So if you double distance, it's 4 times less power.
Right.
The power of all those carriers hitting the antenna is going to be on the order of like nanowatts, right?
Right.
And it would take a lot of carriers or your receive antenna to have a lot of gain or be very close and have all of those performers in the exact same spot in order to get up to 0 dBm.
So at that point, all the normal rules of filtering apply, just not only to make sure you're under the power limit, but also just their normal best RF practices. So if there's a strong TV station in the area that's not,
Absolutely, yeah.
not part of it.
So yeah, and there is a difference between what people can practically afford or carry on their cart and do, and then best practices. Yeah. Best practices, absolutely, would be to have a bandpass filter in between the antenna and the input. If you're doing a single carrier, maybe it would be a high Q, like a tuned cavity filter,
right.
Tuned right around your frequency. If it were multiple carriers in a certain block, you'd want your bandpass filter, around that block. But that being said, that's best practices, and it's great if you have the time, knowledge, and funds to do that. But we do have people every day who don't put bandpass filters.
And they're just putting a shark fin antenna on it and running it out.
Yeah.
And
yeah.
running the fiber thousands of feet, let's say.
Well, 1,000
feet?
Yeah, 1,000
Yeah.
feet maybe.
And not worrying about sort of best practices.
Yeah, not worrying about best practices. It's always best to follow best practices,
right.
but you can you can get away with not following them sometimes. And we do have people. How much time do you think we have left, by the way?
I think 5 more minutes.
5 more minutes? Okay. So we should probably talk about if you do want to use, and this is very common with production sound, if you do want to put an IFB, right? So say your cart is like way outside the village or something, and you want to remote your antenna in a place that so that the entire crew can hear you know, pick up the signal. You do have to change the accessories that you use. You can't just buy a optics package and plug in your IFB or IM transmitter and hope it'll work, because it's not going to work, because it's going to exceed that threshold that we were talking about. So I just came up with this diagram here that shows basically what you need. In addition to the fiber optic transmitter, the receiver, and the fiber strand, you need to have an attenuator in between the IFB or IEM transmitter to get the signal level below that 0 dB threshold. Of course, it would be great if you had a bandpass filter in there as well, you know, your results might vary. And then, of course, that's going to lower, on the other end, downstream, right, the output of the fiber optic receiver is going to be 1 milliwatt. So you need to re-amplify it back up to whatever you want. Of course, you shouldn't exceed 250 milliwatts, but you need to find a low noise amplifier that will compensate for the attenuation that was placed at that input. What else should we talk about? Oh, and then if you want to have, and that was just for a single IFB or a single IEM carrier, okay? If you want to put multiple IFBs, like 4, 8, 12 IFBs, or IEMs into one optics system, it gets pretty complicated. And I think we have time to go over this diagram.
But there are transmit antenna combiners that can be used, right? And then you would attenuate the signal accordingly.
Yeah, I would say if you don't have significant experience, if you want to do an advanced distributed antenna system or multi-carrier transmit application,
and your value-added dealer can help you.
Exactly. Call Gotham. If you don't have that experience, if you don't have a degree in electrical engineering or broadcast engineering, or you haven't been working in the field for 20 years, give Peter a call. Or we're also happy to help as well.
And I think that is 2 separate uses for the system. You know, the receive side is the most exciting for me, partially because it's simple. You know, it's very straightforward. You're not likely to exceed that 0 dBm threshold. And it's, you know, 2 of them will give you diversity. And you put all the RF antenna combining stuff on set and bring via fiber back to the control room. The other way is trickier, and I acknowledge that it's also very useful to do it the other way. But if you think about it, all the same principles apply, like you pointed out. You got to knock the signal down to get into the fiber optic transmitter, and then on the other end, you got to bring the signal back up to transmit via antenna. And yeah, I think that again, you know, you're sort of saving. You know, it's thousands of pounds of coax that these things. I mean that not in currency, but in weight, and then the currency, it could be both. As well. That you're really saving at that point. It's very, very cool. Availability in Europe is one question that we had.
Yes, these are available throughout the EMEA territory through Shure. Shure is our distributor in those territories. So if you live anywhere in EMEA, which is almost anywhere that's not the United States or South America, you can indeed get an optics.
And these are shipping now?
These are shipping now, yes. And this is the second version of this. We had a previous version. This might be my last point. And the updated version includes BNC, connector for the RF input. Previously, it was those tricky little SMAs, right? And then the fiber connector is the easier to find and more ubiquitous ST instead of whatever we had before, which I can't.
And no fancy requirements for the ST, like no angled anything?
Nope, no angled anything. So you want to ask for or put in your shopping cart single mode, 1310, almost all single mode is 1310 nanometer. That's the wavelength of light that travels through the fiber. But single mode terminated on both sides with ST. And that should get you what you want. And as we're demonstrating here, there's all sorts of flavors of ST single mode. This happens to be TAC12, so you can see there's 12 individual strands in this bund that travels through this sheath. But you can also go simple too and just get a single strand as well.
Right. Awesome.
All right.
Alex, thanks
Thank
a lot.
you so much, Peter. A pleasure.
Thank you. All right, so thank you for tuning in. I'm just going to check for last minute questions and nothing there. Next Tuesday, February 16th, tax and finance update for production personnel. We have Nancy Adams and Ann Johnson here, and they will give an update to the seminar we did a year ago. So this will be, it's excellent. If you freelance or if you are involved in content creation or distribution at all, you should definitely check it out next week. Archives at vimeo.com/GothamSound and Facebook and Twitter as well. Ideas, please send them to info@gothamsound.com. Thank you for tuning in, everybody.